Good morning, our students, and welcome to this morning's discussion. Today, we'll be talking on sampling distribution of sample means. And we are going to talk about it under two categories when sampling is for with replacement and when sampling is for without a replacement. So, it is very necessary that we understand the concept of with replacement and without replacement as it concerns sampling. And for that note, we are going to talk about the population, and then this population has size what n. Then we equally talk about sample, and then this sample has a size small letter n. The same thing applies here. We talk about population. This population has a size capital N. Then we talk about the sample, and then this sample has a size small n. So when sampling is for with replacement, and you come to a population of size n, and your interest is to draw a sample of size small letter n, what is going to be done here is that as you are drawing a unit from capital N into small n, which is your sample, each of the elements or unit that you draw from this population capital N into this small letter n is returned before you draw the next one. When it happens that way, we say sampling is for with a replacement. For instance, coming to a population of 100 scores of a student, capital N is 100, and trying to draw a sample of size 5, that is 5 scores from these 100 scores. If you come to these 100 scores with the interest to draw 5 scores to form your sample, each score you draw from that population of 100 scores into this small letter n is returned back before you draw another one. When it happens that way, we say sampling is for with replacement. However, when you come for without replacement, and then you have 100 scores and equally you want to draw 5 scores. You come to this 100 score, you draw the first one. That first one you have drawn there is removed from the population before you draw the next one. And then after you are done with the next one, you still remove it now before you go to the next one. And you continue in that order till you get your 5 scores into your sample. When it happens that way, we say sampling is for without a replacement. Now, when you have a population of size n and then a sample of small letter n, and sampling is done for with replacement, we usually ask ourselves, what is the possible number of samples that we can draw from this population of what of a size capital N when sampling is done for with replacement? The total number of samples that can be drawn there is given as capital letter N raised to power small letter n. So if your n here is 20 or 100, and then your n here is what 5, and you are now asked to find the total number of samples that can be drawn from this population of size n, each of size what 5. It will be given as 100 raised to power 5, and whatever number it gives you is the possible number of samples we can draw there. And each of the sample that is coming from there has a probability of capital 1 all over capital letter N raised to power n. So this is the total number of samples that can be drawn when sampling is done for with replacement, when the population size is capital N and then the sample size is small letter n. and this is the probability of each of the samples that are drawn. However, when sampling is without replacement, the total number of samples that can be drawn there changes, and it becomes, this is now given as capital letter N combination what? Small letter n. So if n here is 100 and then the sample size is what? Is 5. Then you now end up going to know that the number of possible samples that can be drawn there is 100 combination 5. Whatever thing now you get here is the total number of samples that can be drawn from a population of capital N, where each of the sample is what? Is 5, when sampling is for without replacement. And the probability of each of the sample will be given as 1 all over n combination what? Capital N combination n. That is the probability. Now let us now return back here to lay emphasis on what is meant by sampling distribution of sample means. For instance now, that when you now get this your n raised to power n, where this your capital letter N might not necessarily be 100, and this your N might not necessarily be what? Be 5. They can take any value. But let us say that when you come here, then you now check the number of possible samples you can have here, and then you now say N, capital N raised to power N, and you happen to have something like, let me say 25. Let me put it that way. It means that you are going to have 25 samples. And in these 25 samples now, you are going to calculate the mean of each of the sample. Let us say that the first mean of the sample is given as x bar 1. The second one is given as what? X bar what? 2. Then the third one is given as x bar 3. Down to what we call x bar 25. That is 25 means coming from the 25 samples. Let us equally say that you came over here and whatever the value of what of capital N and whatever the value of what of small letter n, you happen to equally have something like, let me even say, still 25 what samples. And then you equally have what is called your x bar 1, you have your what? X bar what? 2, you have your x bar what? 3, down to x bar what? Bar 25. Now you find out that this x bar 1 is likely going to be different from x bar 2. X bar 2 likely going to be x bar what? 3 down the line. So the means will now differ from sample to sample. The same thing applies here. And because the means are no longer constant, instead they are changing from sample to sample, we say that they form a distribution because it's now a random variable. They form a distribution. And that distribution that is formed by these means coming from these different samples is what we refer to as sampling distribution of sample means. So anytime you hear about sampling distribution of sample means, let your mind goes to the distribution of means coming from different samples drawn from a particular population, and each of that sample have the same sample size. That is what we mean by that. And do remember that when we talk about a distribution will equally have a property. And that property is what we are now going to describe. So we are going to talk about properties of a sampling distribution of sample means. Properties of sampling distribution of sample what means. So you are going to permit me to clean here and clean here while we talk on the sampling distribution of a sample means. So permit me to clean here. Okay. Now let us now say that you now come to this population. And when you have come to this population now, that population has a distribution, and that distribution is in terms of the mean and the variance. Let us say that the mean of the population, mean is given as what? As what? Mu. And then the variance is given as sigma squared. And then from a population that have these characteristics, the mean is mu, the variance is sigma squared. You draw up to what? Up to 20 samples or 25 samples like we said earlier. And these 25 samples you are now having as, you have your what? Your x bar 1, comma, x bar what 2, comma, x bar what 3, comma, down to what? X bar what 20 what 5. You equally come to this population, and this population equally has a mean. The population has a mean given as what? Mu, and then the variance is given as sigma what squared. And from that population, you equally draw 20 samples. And from the 20 samples, you compute the means, x bar 1, x bar 2, up to x bar 25. So you are going to have your what? Your x bar what? 1, x what bar what? 2, x bar what? 3, down to x bar what? X bar 25. When we talk about remember that this has formed a distribution and this thing has formed a distribution. And because they form a distribution, we will be talking about the properties of that distribution equally. And when we talk about the property of that distribution, what we are saying is, what are the mean and the variance of these distributions now formed by these samples or by the means of these samples? Now we are told that if sampling is done for with replacement, that the mean of these means will give us a population mean. That is what they say. The mean of means will give us the population what? Mean. And when we talk about the mean of means, we are saying the expected value. So what they are saying is that E of what? X what bar? E of X bar. This E of X bar is what we call expected value of the mean, and it can be called here the mean of these random variables. So, or the mean of these random variables now, which is given as, we now have what is called what? Summation. Or let us not even use summation. We have what is called mu of what? X what bar. This is given as what? As mean. So by implication, we are saying that when we say summation, that I is running from 1 to what? To 20 what? 5 of x what bar what I all over 25, that the answer is going to give me mu. That is what we mean by mean of means. That when we come to this distribution and we obtain the mean of this distribution, the answer is going to be the same thing as the population mean. The same thing applies here, that when we come here and we say E of X what bar, which is given as mu of what? X bar, is given as equally as what? Mean. By implication, that summation that I is running from 1 to what? 25 of X bar what? I all over 25 is going to give me what? Mean. So if you count a distribution that has mean mu, you take a different samples, you compute the means of these different samples, and you obtain the mean of the means. The answer is going to give you the mean of that population. However, they are different when you talk about what the variance. So you permit me to clean that of what the mean, and we'll talk about that of the variance. So permit me to clean here. So now we have talked about the mean of this distribution, which you have shown that it is the same thing as the mean of the population. We have talked about the mean of this distribution, which you have shown that it is the same thing as the mean of the population. What happens to the variance of this distribution? When samples are taken from a population with mean mu and variance sigma squared, and then we get their means, and their means form a distribution. And we are now interested in the variance of that distribution formed by these means. It is given as, the variance is given as var of what? X bar, which is the same thing as saying sigma what squared of x what bar, which is the same thing as saying sigma what squared all over what? N. So, the variance of the distribution formed by the mean, okay, by what? By the means of samples taken from a population capital N, each of the sample with size n, when sampling is done for with replacement, the variance is given as this. That is the ratio of the population variance all over the sample size what? N. When the sampling is for without replacement, the variance is going to be given as var of what? X what bar, which is as sigma what squared of x bar is given as, we have sigma what squared all over n multiplied by capital what? N minus n all over capital what? N minus what? 1. This our capital N minus n all over capital N minus 1 is what we call finite population correction factor. It is called finite population correction factor, often written as FPC. So anytime you see they write FPC, they are talking about finite population correction, even though it is called finite population correction factor. But that F is not always written in the abbreviation at the end. So there is a difference between the variance here from the variance here. And then let us now pay attention to see the behavior of this. Of course, it can be seen here that when we are increasing, the name that is given to the variance of this distribution is what we call the standard error. It is called what? The standard error, or what we call the variance of the sampling distribution of means. Variance of the sampling distribution of means. The same thing applies here, variance of the sampling distribution of what? Of means. Now, of course, we can see that when the sample size here is increasing, the variance is meant to be decreasing, because the variance is sigma squared all over what? All over n. So when this sample size n is increasing, because it is at the denominator, whatever value that is here is constant. So as you are increasing the sample size, this value here, if you divide it now, it will be coming down. So the larger the sample size, the smaller the variance of the sampling distribution of what? Of means. However, the smaller the sample size, the higher the variance of the sampling distribution of sample means. Another interesting thing here is that if we know the variance of the sampling distribution of sample means, we can equally find the variance of what? Of the population. For instance, what we have here is that var of x what bar is given as sigma squared all over what? N. I can make this sigma squared, which is the variance of the population, a subject formula. And then this thing becomes as sigma what squared is given as n multiplied by this is n var of what? Of x bar, this way. So if I am told that the variance of a sampling distribution is 5 or is 1.2, while the sample size is 30, that I should find the variance of what? Of the population. I'll just say here is 30 multiplied by 1.5. Whatever value it gives me is what we call the variance of the population. And I can equally know the variance of what? Of the sampling distribution of the sample means. The moment I know the variance of the population and equally know the sample size. So if they tell me in a question that the variance of a population is something like a 4.5 and then the sample size is something like a 25, what is the variance of a sampling distribution when the sampling is done for with replacement? I will come and then I will fix the value here. The same thing applies here because we can equally begin to make subject of formula in this particular place. However, we are going to make something clear here. Let us now come to this one and then we see the behavior of this one. When the sample size is very, very small, in fact, when the sample size here is 1, let me put it this way, you find out that here becomes n minus 1 all over n minus 1. And then here, what I'm going to have at the numerator becomes exactly what I'm going to have at the denominator. And then if I divide, I am now going to have 1. And 1 multiplied by this will give me that thing. By implication, when the sample size is very, very small, relative to the population water size, then my finite population correction factor now tends to what? To be 1. And then the variance of the sampling distribution when sampling is for without replacement now becomes exactly as the variance of the sampling distribution when sampling is for with replacement. So when the sample size is very, very small relative to this particular thing, one can equally ignore the finite population correction. However, when the sample size continues to increase, then you find out that this numerator here now continues to become lesser and lesser and lesser. And when it becomes lesser and lesser and lesser now, and you keep to divide it with this constant under here now, the value will continue to go down and go down towards what? 0. And then it will now affect this quantity when you use it to multiply this quantity. So when the sample size is very small relative to the population, then the finite population correction tends to 1. But when this sample size now becomes what? Very, very large relative to what? To the tending towards what? To the population size, then the finite population correction factor now continues to tend towards what? 0. So one can easily say that this thing lies between 0 less than f p what c less than or equal to what? 1. That it lies between what? 0 and 1, where it can equally become 1 when the sample size become 1 here. It now becomes exactly 1. So these are what we call the sampling distribution of the sample means. So we now quickly ask ourselves, now what if now somebody just asks us now to calculate the finite population correction factor? The moment we know the population size and we know the sample size, we can easily calculate it because it is just this minus this all over n minus 1. However, I want to show something so that you now see why at times you see this thing this way and equally in some other places now you see it differently. Let me show you something here. So permit me now to clean this place. Permit me to clean here. And permit me to clean here. When we are not talking about variance again, we are talking about standard deviation. And we are not talking about variance, we are talking about standard deviation. And then the interest is that you have come to a population with size capital N. You have now taken different samples, each of size what? Small letter n. And then this population has mean of mu and variance of what? Of sigma. And you have obtained this your means and they have formed a distribution. What is now the variance of this distribution? And what is the mean of this distribution? The mean of this distribution still remains the same thing. It is still going to be E of x bar is given as mu of x bar, which is given as what? As mu. But the variance is going to be this way. The var of what? X what bar is given as, we now have what we call sigma all over, or let me put it this way now. Here becomes what? Sigma was squared all over what? N. You put all of them in square root. Reason, for us to get this sigma here, it is square root of variance what we had earlier. So in that case now, we are going to take the square root of variance that we had before, and this is going to give me what is called what? Sigma all over square root of what? Of n. And then what they now call this thing is what they call the standard error of the sampling distribution of the sample means. Standard error. So you hear this language a lot, the standard error of the sampling distribution of sample means. Okay? It is just the standard deviation of the population all over the square root of the sample size. Then when you come to this one, the mean still remains what? E of x bar is given as what we have as what? Mu of x bar, which is giving me what? Mu. However, you can equally have something that the variance is now going to be var of what? X what bar is given as. You have square root of sigma squared all over what? N multiplied by, you now have what? Capital N minus what? 1 all of minus n all over capital N minus what? N. And of course, this thing which I wrote here can be put this way. This thing which I wrote here can be put this way. It can be put as sigma alone all over square root of what? N multiplied by, you have square root of what? Capital N minus what? N all over what? N capital N minus 1. So you still find some persons where they call this square root of capital N minus N all over capital N minus 1 as the finite population correction factor. It is called that way when the interest is not on the variance of the population, instead the interest is on the standard deviation of what of the population. So anywhere, anytime they ask you a question referring this thing as the finite population correction factor, they are correct. They are coming from the angle of what? Of the standard deviation of the population. But anytime they talk about what? Capital N minus N all over capital N minus 1, they are equally correct, but they are coming from the angle of the variance of the population instead of the standard deviation of what? Of the population. So these are what we call the sampling distribution of the sample means. When sampling is for with replacement and when sampling is for without replacement. Let us now show one or two examples under this, some examples under this. Okay, so they gave us a question here. The question they gave us here says, and I write, the question says, okay, the question says, consider a finite population of size 6. Consider a finite population of size 6. Finite population of size 6. So the population now, capital what? N is equals to 6. If a sample of size 2, if a sample of size 2, so N is equals to what? 2. If a sample of size 2 is to be taken from it with replacement, what is the number of all possible samples? We have given this thing earlier. That the formula for all number of possible samples when sampling is done for replacement is given as capital N raised to power small letter n. This is equals to, our capital N here is 6, our small letter n here is what? 2. So this thing becomes what? 6. That's what it is. So the possible samples that can be drawn from a population of size 6 when each sample is to be size 2 is 36 in number. We consider another question very fast. And that question says, find the number of all possible samples from a population containing 80 items. So capital N is equals to 8. Containing 80 items, from which 2 items is selected without replacement. So my N is equals to what? 2, and it is for without replacement. We have given a formula for that without replacement. It is given as capital N combination what? Small letter n. So this is going to be, my capital N is 8 combination. My small letter n is what? 2. So whatever value this 8 combination 2 gives you, you can check it. What we have here is what? 28. So you are going to have 28 samples, possible samples that you can draw them. And each of the sample has a size what? 2. That is what is meant there. Okay? Let us equally take another example very fast. Okay? This question number 4 says, A population has 10 items. A population has 10 items. So a population n is equal to 10. Okay? Has what? 10 items. And sample, it has 10 items, and a sample has been selected from it containing 5 items. So n is equal to what? 5. The question says, find the finite population correction factor. Find the finite population correction factor. Find the finite population correction factor. The thing we are going to advise you here is that you stick to the one that has what a square root here this time around. So this is now going to be given as, we gave that formula the other time, that it is given as square root of capital N minus N all over what? Capital N minus 1. So this is going to be, so my capital N here is what? Is 10, minus here is what? 5, all over here is what? 10 minus here 1. So this is square root. So this is going to be square root of what? 5 all over 9. So square root of 5 all over 9 is the finite population correction factor in that particular thing. Okay? Let us quickly look at this example again. So there is also a question here that we are going to pay attention to. And that question says, okay, that question says, a population contains 2 items. A population contains 2 items. So n is equal to 2. Okay? They now say, and a sample of size 4, our n is equal to what? 4. Is selected from it. What is the possible sample size? Let me say something quickly here. In a situation whereby you see that your sample size is larger than the population, what kind of sampling are you doing? Is it sampling for with replacement or sampling for without replacement? The answer is sampling for with replacement. Because it is only when you are sampling for with replacement that you have the chance of selecting items more than the population. For instance, if the population is 1, 7, and 9, the population is 3, and you want to select the sample of size what? N, small letter n is equal to 5. You come to the first one, you sample this one. You return this one here. There is also a possibility that when you want to draw from that sample, you can still obtain 1. You return that 1 back, you can obtain 7. You return that 7 and you want to draw again, you can equally draw 1. You return that 1, you can equally want to draw, you draw 7. So it is only when you are sampling for with replacement that your sample size can be greater than the population size. So in this context now, one can easily say here that our n is greater than or equal to what? Capital letter N. Do you understand? There is a possibility that n can be greater than or equal to this. But in this particular one, n is always less than or equal to capital letter N. You cannot go beyond what? N. So you should pay attention when you see this kind of a thing. This is for with replacement. This is for without replacement. To avoid making this class very, very large, we, in our next question, stay connected and tuned. In our next question, we are going to look at the sampling distribution of the difference between 2 population means. Thanks for your audience.